Let's continue learning about beam equations. So we looked at a very infinitesimal beam element like this, and we applied we looked at the distributed loads and moments and shear forces at a very small distance dx, and we found these equations, the relationship between the distributed force Wx and shear force V. So Wx is equal to minus dv over dx, which is the derivative of shear force with respect to x, which is the length or distance along the length of the beam. And then we said that v is equal to dm over dx, which is the derivative of moments with respect to x, again, the distance along the length of the beam. This tiny point of a beam could be a point like that in a deformed beam. And this green line, again, is the neutral line of the beam. And for that point, we can define a radius of curvature. So it looks like a circle, and we can have a radius for it that we show with rho. And here we could look at it in a magnetized or increased size to see that there is dx, which is the length of that infinitesimal beam, and it could also be equal to rho d phi, and d phi is the rotation of that infinitesimal element in the beam. And the reason that dx could be equal to d phi is that d phi is a very small angle. For very small angles, we know that also sine d phi is equal to tangent of d phi, which is equal to d phi. So we can assume that rho d phi, which is the length of this portion, is equal to dx. So we can write rho d phi is equal to dx. And as a result, rho becomes dx over d phi. Or we could rewrite it as 1 over rho becomes d phi over dx. 1 over rho is what we call curvature of a beam. So this is called curvature. And it's also equal to m over ei. M is the moment, E is the Young's modulus, and I is the second moment of inertia. And so what they will give us is this equation. M over ei from here is equal to d phi over dx from there, because they're both equal to 1 over rho. We also know that phi, the angle of rotation, is equal to dv over dx. V is displacement in the y direction, so displacement in y direction. And x, again, is the distance along the length of the beam. So we end up with this equation. M over ei is equal to d2v over dx squared. So, knowing this equation from the previous slide, and we also knew that v is equal to dm over dx, we could insert that in here. So v is equal to d over dx of ei d2v over dx squared. And if we assume that ei is constant, so we can take it out, then v, the shear force, becomes equal to ei dv3 over dx cubed. So this capital V is the shear force, and this lower v is displacement in y direction. It's important not to confuse them. And actually, this v is the displacement function similar to u that we had for trusses and springs. So we're going to have to find the Vx for a beam in the future to find the stiffness matrix of the beam. From before, we also know that Wx, the distributed forces, is equal to minus dv dx. So if we bring that equation in here, we will know that Wx becomes minus ei times d4v over dx to the power of 4. And if there is no distributed loads applied to a beam, then that equation becomes simply 0. So we found the equations that would relate the forces to displacements. So basically the forces and displacements and the forces and displacements can be found from these two equations. Next, we'll move to find the displacement function for a beam and move on to finding the stiffness matrix of a beam.